For the semester project, I performed a least cost path analysis to select a route for a pipeline. As you will see in the presentation, the project is about using the least cost path analysis method. The actual pipeline is hypothetical. Since pipelines travel long distance, variations in terrain and population affect the route selection. The goals in selecting any route typically include minimizing construction cost, ensuring public safety, and minimizing impacts to the environment. The costs and the input criteria for the least cost path analysis reflect the goals established in the construction project. For example, in minimizing construction costs are increased by water crossings because the pipeline must be bored underneath the water or a bridge must be built to cross over the water. Construction costs are also increased by changes in elevation of the terrain. Initial costs may also be increased when leasing the right-of-way for the pipeline. Highly developed areas or land under cultivation incur higher costs than undeveloped land. When considering ensuring the public safety, population density affects the operating parameters of the pipeline once it is in construction. In high population areas, the allowed operating pressure of the pipeline may have to be reduced. Avoiding high population where possible is an advantage when selecting the initial route. In efforts to avoid harming the environment, minimizing water crossing also helps reduce potential risks to the environment. A pipeline leakage at a water crossing compounds the impact on the environment since the water may be contaminated as well as spread the pollution. Environmental impacts are reduced by avoiding wetlands or other environmentally protected areas. This project will find and evaluate a route for a pipeline from a desired beginning to ending location using least cost path analysis in a geographic information system. The analysis is performed in Esri ArcMap. The criteria used in the project will consider the elevation changes in the terrain, the land cover, and the population density. Since the project is about a hypothetical pipeline, the study area in the project is arbitrary. An area in Texas that exhibited variation in the three criteria was selected. The source and destination points for the route were selected at the extreme ends of the study area. Since three criteria were used in the route selection, a route defined by each separate criteria was compared with the route found from the combination of the three criteria. The results were evaluated by looking at the total mileage of each path, the number of schools within a buffered zone of the center line of each least cost path, and comparison with a straight line path between source and destination point. The data used in the project came from the USGS National Map, a 100-meter resolution digital elevation model provided the elevation values. A 30-meter resolution raster dataset of land cover was obtained from TNRUS. Population data at the block group level was obtained from the 2010 U.S. Census. Urbanized areas were viewed using urban polygons in Texas, also obtained from TNRUS. Point locations of schools for the final evaluation of the route selection was obtained from Esri Data and Maps website. The goal in choosing the study area was to find variation in all three criteria: elevation, land cover, and population. Visual inspection of the DEM in Texas shows high variation in the Big Bend area, but not much variety in land cover or population. The vicinity of San Antonio exhibited wide variation in elevation, population, and land use. A circular area of approximately 7,400 square miles was selected as the study area. Zooming into the study area shows 16 counties, which cover the 7,400 square miles, centered around San Antonio, which is in Bexar County, and there's highly populated areas between San Antonio and traveling up toward the Austin area, which is just outside the study area. The source and destination points were selected to be at opposite ends of the study area and to be on opposite ends of the high population area. In performing the least cost path analysis, first the cost rasters were developed to reflect the goals of the project: minimizing construction costs, ensuring public safety, and protecting the environment. A cost value was assigned to each cell in the raster. Second, a cost distance raster was developed to find the least accumulated cost from traveling cell to cell from the destination cell. The cost between cells is the average of two adjacent cell costs times a factor of 1 or a factor square root of 2 for diagonal cells. Third, in calculating the cost distance raster, a backlink raster records the directions of the least accumulated cost from the destination cell. The least cost path is found from the cost distance raster, the backlink raster, and specifying the source cell. The diagram shows the least cost path analysis process. The first step in the process is developing the cost raster for each of the criteria. The Reclassify tool under Spatial Analysis Tools in ArcMap applies the cost to each raster cell. In this project, a ranking system is used to rank the cost from 1 to 9. In assigning a cost to the elevation is first converted to slope values using the Slope tool. The Reclassify tool applies the cost rank to ranges of slope values. The gradual slopes receive the lowest rank, and the higher slopes receive the higher cost ranking. By comparing the slope cost raster with the DEM, it is apparent that the flatter terrain receives the lowest cost values, and higher terrain shows the steeper changes, which equate to higher cost ranks. The land cover cost raster was developed by assigning cost rankings to the type of land cover. The metadata for the land cover raster defines the land cover type. In this project, rankings were chosen to reflect the goals of minimizing construction costs. So open water and high-intensity development received high ranks. Cultivated land received medium cost rankings. In order to reduce environmental impacts, again the open water received high ranks, and wetlands also have high ranks. These rankings could be modified to suit the goals of any project. The land cover cost raster is developed from the reclassify tool. The open land shows the lowest cost. The open water and high development have the highest cost rank. The population density raster had to be developed from the vector data sets of the counties at the block group level. The 2010 census population data was obtained from the American Fact Finder data under the total population in occupied housing. The polygons of block groups was obtained from the 2010 census Tiger line shapefiles. The 16 county shapefiles were merged and converted to a raster based on the population density values within each block group. A raster size of 100 was used to match the resolution of the elevation raster. The raster for the study area was extracted and then reclassified with high population density values receiving the highest cost rank. The low population densities translated into the pink area indicating low cost. The high population density in San Antonio and the land between San Antonio and Austin show up as the higher cost ranks. The cost distance tool was used with the selected destination point for the pipeline route. A cost distance raster was found for each of the 3 separate criteria. The 3 criteria were combined into one cost raster using the weighted overlay tool. The overlay tool allowed for weighting of the input cost rasters. 60% was applied to the population density cost raster, 20% to both the slope cost raster and land cover cost raster. This weighting could be different depending on the project goals. Once the combined cost raster was developed, the cost distance raster with the assigned destination was found. The cost path tool was used to find the least cost path from the source location to the destination location. The cost distance raster and backlink raster was used to find the least cost path for each of the criteria and for the combined criteria. The least cost path was converted to a polyline for evaluation of the routes. And this slide shows the combined least cost path. The paths found in the analysis were overlaid onto the 16 county study area for comparison, along with a straight line path from source to destination. When the elevation criteria alone was used, the route found went through the highest population area. The land use and population criteria went around the highly populated areas and highly developed areas, as did the combined criteria. The total mileage for each route was found using the Calculate Geometry feature in ArcMap. The straight line path showed the least mileage. However, the lowest mileage does not necessarily mean the lowest construction cost. The least cost path analysis allowed for reducing water crossing, reducing changes in elevation, and lower population density. The data set of point locations of schools was overlaid onto the paths, and the proximity to the schools was used as a means to evaluate the routes with respect to public safety. A buffer was applied to each route, and the number of schools falling within the buffer was counted using the Select by Location tool. First, a 660-foot buffer was applied, and then a second buffer of 3 times the 660-foot buffer. The value of 660 feet was taken from the regulatory requirements on gas pipelines. This table shows that the straight line path encounters more schools than any of the other paths. The path based solely on reducing elevation change encountered the next highest number of schools. The population density criteria and the combined criteria encountered the least number of schools. As stated, the population density carried the greatest weight in the combined analysis. This project illustrates a method for applying multiple criteria for a least cost path analysis in a pipeline route selection. The costs and weights assigned to different criteria based on the project goals ultimately defines the route selection. The shortest path had the greatest impact on public safety. The next shortest path impacted public safety the least. The combined criteria was weighted more heavily with the population density, but had a longer path due to the land use and elevation change. The outcome of the least cost path analysis could be different with different cost rankings assigned in the land cover cost raster, or the weights assigned in the overlay raster could be modified. The project illustrates the power of the least cost path analysis, especially with the capability to tweak the input parameters depending on the project goals.